So the next topic is called power series. Power series. Sounds fun, huh? Okay, so let's just first a note. So this is our geometric series, right? This is like the first kind of series we learned. So can you write out the first four terms, or tell me what this means, right? Can you write out what this means? So when you see that, you think what? Write it out. You see that, you think what? Write it out. And if you can't do that quickly, then you're not catching on to series. Okay? No, this is all notes. Okay, so we see that, we think what, Brandon? AR times AR to the n? Yeah. He wants AR times AR to the n. Is that what you think when you see this? No. Okay, Brock, when you see this, what do you think?
The sum of AR to n minus 1 starting with n equals 1.
Which is what? What is that?
The sequence.
It's not a sequence. When you see that, you think what? Okay. A plus AR squared plus AR cubed. If that's not what you were thinking, then you need to quick. When you look at series, you need to think of this way. There are an infinite sum of terms, and you need to be able to write out the terms no matter what series you're given. Okay? So again, don't get lost in the rules and the algebra and the memorization. You still have to hold on to the meanings of things, right? So see this, think this. Okay, so now, how could we write this with the index starting at 0 instead of 1? So this now, for this starting at 0 over here, so we want this one to be for n equals 0, and then this for n equals 1, and then this for n equals 2, etc. So what would you write here? So that you get the exact same sum. It's the exact same sum. It's totally equal to this, but it's just we're going to start the index at 0 instead of 1. That should be an easy exercise. So what formula gives you A when n equals 0, gives you AR when n equals 1, gives you AR squared when n equals 2, etc.?
Easy, right? AR to the n.
He wants AR to the n. Agree with that? Okay. AR to the n. So here, this is another way to represent the geometric series. Instead of n starting at 1 and the first exponent being, or the exponent being n minus 1, you could start at 0 and the next one would be n. Why? Because both those sigmas give you the same sum. Make sense? Okay, so lots of these power series, the reason I make that transition is lots of these power series then, or lots of series that we'll see from now on, they will start at n equals 0 instead of n equals 1. But the exact same series could be written both ways. The exact same series could be written starting at 0, starting at 1. Okay, that's just a note. So now let's talk about power series. So a power series is a series of this form. The terms are C sub n x n. So when you see that, you think what? Go. You see that, you think what? Write it down. Okay, Patrick, you're up.
So the initial value of C plus second value of C times x plus third value of C plus times x squared.
Okay, and then are all the C's the same? Is it always the same C?
No.
How do you know?
Because the subscript of n means it's a changing value.
Right, so you don't want to just say C, because if you just said C, like the way you said it verbally, it would mean the same value. So you want to say C sub 0 plus C1x plus C2x squared plus C3x cubed, etc. Okay, so let's observe some things about this. First of all, like we just said, you have changing coefficients depending on the value of n. So that coefficient is a formula, could be dependent on n. Right? And what else? So there's something new here about this, different than all the other series we've seen before. What's different about this one?
X.
Two variables.
Well, only one. Yeah, so if you're counting n as a variable, n is our index, not really a variable. But yeah, now you have input variable, right? X is an input variable. Meaning x can change. For different values of x, you get different series. So what this is like a whole family of series. So for any x that you choose, you get a different series. So this is the idea of a function, right? So this is like a polynomial function, right? But it's unlimited. Unlimited number of terms. It just keep adding terms. So these power series, since you have this input x, they're like a function.
So is C sub n some expression in terms of n?
Yeah. It depends, right? It's changing coefficient depending on n, depending on which term you're at.
Cool. So how do you know what to use for C? You would actually sum them up.
Well, they'll tell you. They'll give you.
Yeah, no, so this is just the general form for all power series. So this is what they all can be written as. Okay, so then we've got this input variable x, right? So depending on what x is, you get a different series. So if x is 1, you get a series. If x is 5, you get a series. If x is -1, you get a series. So then that begs a question, right? So what question does that beg?
Which x?
What's that?
Which x?
Which x?
Or which series of x is going to converge?
Right, good. So for what values of x will the series converge, and what values of x will it diverge, right? So that's the question. That's the main question here. What x do we need? What values of x will make it converge, and then of course the rest will make it diverge, right? Because we're interested in series converging. That's more interesting than series diverging, right? So we want to know what x make it converge. Okay, so here's an example. So what is C sub n in this power series? What is C sub n?
1 over 2n minus 1.
He wants 1 over 2n minus 1. Agree with that? Yeah, because you got your x to the n. So 1 over 2n minus 1 is this C, that's your coefficient. Okay, so how are we going to find out? We want to find out for what values of x this converges. So, what do we have to figure out how if the series converges or not?
Various tests.
Tests. Okay? And so for these power series, the ratio test, okay? That's what we called it, right? Yesterday? Okay, the ratio test. So we use the ratio test to find the values of x for which the series converges. Okay, so the first step looks like this. We've got our n plus 1 term times the reciprocal of the n term. You did some homework like that, right? Does that feel familiar? Yeah. Okay, so how do the x's simplify? You got x to the n plus 1 over x to the n. Just an x, okay? And then what will we have in the denominator? That denominator will be 2n what?
2n plus
2n plus 1, right? So we just get our x, and then we're going to have 2n minus 1 over 2n plus 1. Okay, now we're ready to take the limit. So what's the limit of that ratio there, the first ratio?
It's x. Oh, well, yeah, it's x.
So, because the ratio, limit of the ratio is? Just the first
Oh, the first box, that's a
quotient.
1.
1, okay, you got the limit of 1, and then x doesn't care what n does, it's just x. So this is just absolute value of x, right? This limit. So, we need this limit that we started with to be what in order for this series to be convergent?
Less than 1.
Right, we need the limit to be less than 1.
Oh, yeah.
Right? That's the rule. If it was greater than 1, it diverged. If it was equal to 1, the test had no conclusion. And if this limit that we set up is less than 1, then we get convergence. So that's what we want. So we want this absolute value of x to be less than 1. And then for those values of x, it will converge. So what values of x is that? When the absolute value of x is less than 1, how do we say what values of x is? Negative 1 to 1, right? Negative 1 to 1. Make sense so far? Okay, but what about negative 1 and 1? We need to check these separately. Okay? So at the endpoints of our interval, this is called the interval of convergence. But those endpoints, the series may or may not converge at those endpoints, and we need to check them separately.
Why?
Because the series may or may not converge at the endpoint.
Right, but why do we know that? Why do we know that it may or may not?
That's just what happens, right? So we've got this interval of convergence. Outside the interval, we have divergence. So at the endpoints, it could converge or diverge.
Okay.
That's just what happens. Yeah. So it's like, what is the breaking point? Is it the open interval or is it the closed interval? Depends on the series. Okay. So let's do x equals negative 1 first. So what series do you get when x equals negative 1?
Well, we get
Harmonic.
we'll get well, we get 1 over
Oh, wait, no. It's alternating.
1 over
No, right? It's going to be negative 1 to the n, right? Over 2n minus 1.
yeah.
So you just plug in x equals negative 1, and now you have a series like the ones we've done before. Okay, so this is alternating. So we can think about the alternating series test. So what are the conditions? That the rest of it, the non-alternating part, okay, is what? Decreasing, and the limit is 0. Do we have both those conditions met here? 2n minus 1 over 2n minus 1. Is that decreasing and limit of 0?
Absolutely.
Yeah. So 1 over 2n minus 1 needs to be decreasing, check, and limit 0, check. Therefore, convergent or divergent?
Absolutely convergent.
It's not absolutely convergent. The alternating series test does not check absolute convergence. It only checks convergence.
Okay.
The ratio test would check for absolute convergence, but the alternating series test only checks for convergence.
Okay.
Does not check for absolute convergence. Okay? But we have it, right? So it meets the criteria of the alternating series test.
So negative 1 is the
Negative 1 we're going to put in the interval for possible x values that make this thing converge. Okay? So now we've got x equals 1. What series do you get when x equals 1?
just 1 over 2n minus 1.
1 over 2n minus 1, right? 1 to the n is always just 1. Okay? So when x equals 1, you just put 1 over 2n minus 1, and then we ask this question, convergent, same question, convergent or divergent. What do you suspect? All right, so what would you divergent because it's similar to?
Harmonic.
Yeah, so we're multiplying it by 2 and we're subtracting 1, but in the grand scheme of things, that's not going to, that's still, it's essentially the same as a harmonic series, right? So how can we show that? I mean, that's what we suspect, and that's good reasoning. But if we want to show that outright, here's what we can do. So here's a trick. I want to factor out 1/2 first. So if I took a 1/2 out of that, I'd get 1 over what? N?
Can you take it out all the way, like in front of the sigma?
Sure. So minus what?
Minus 1/2.
1/2. Now he wants to bring the 1/2 out in front, and then you can do that because every term is multiplied by 1/2. So I can take that out, and so it's really irrelevant, right? Because if the thing converges, then 1/2 of that sum is convergent, of course. If the thing diverges, then 1/2 isn't going to converge; it's still going to diverge. Okay? So the 1/2 is kind of inconsequential now, and we look at this. How do the terms 1 over n minus 1/2 compare to 1 over n? What is that compared to 1 over n?
Always less.
Less. Is it less?
Goes to 0, lower.
No, just 1 over n minus 1/2 compared to 1
Oh,
over
so
n.
it's greater because you're dividing by less.
You're dividing by a smaller number, so it would be. Isn't it greater?
Yeah.
So what do we have? We have a series, all of whose terms is greater than the series 1 over n.
This is comparison?
This is comparison. But this is using comparison to show divergence, right? So, which is fine. So this series diverges, and then you have a series all of whose terms are greater than that. Conclusion? Divergent, right? Divergent. And that's what we suspected. You know, we said this is essentially the same as harmonic, but this now proves it, okay? We prove it because we say every term in our sequence is greater than the terms of a sequence we know diverges, therefore it has to diverge also. And that's comparison test for divergence. So if you have a sequence, all terms all are greater than or equal to a sequence whose series diverges, then yours diverges also.
So greater than or equal to -1, less than 1.
Oh, so you're making the conclusion. Yeah, so that's x equals 1, divergent, right? By comparison to 1 over n, basically.
If I want to say for all, is that the upside down A?
For every, yeah. Okay, so then we've got, this is what's called the interval of convergence. We include -1, but we don't include 1. So if we put that on a number line, okay, we get this. Okay, and if we think of this, so this interval is centered at what? This interval is centered at 0. And so, and it extends out 1 in each direction from 0. So we can kind of think of this like a circle, right? So the radius of what?
1.
Radius of 1. So the interval of convergence is from -1 to 1, and then you have what's called the radius of convergence. And so what's the radius of convergence?
1.
1.
What?
Okay, so your interval will be centered on some value, and then so the distance from that center value out to the end is what you call it's called the radius of convergence.
What is that for?
What is that for? Because it's just because you always have a center and then an interval out from that. So so the width of your interval will be 2 times the radius. I don't really know where they came up with the need for that in the first place, but it's a question you'll be asked. Okay? But you can think of it this way, as like on a number line, and then think of a center and like a circle. And that's the radius. Okay, questions on this example?
I have a question.
Please.
Those 2 check marks that you were referring to,
Yeah.
the alternate series test, I didn't catch what those were. Increasing 0? Is that what you said?
Yeah, so that was, we covered alternating series test yesterday. So the first condition alternating series test is that it's a decreasing sequence, and that the limit is 0. And if both of those conditions are met and you have it alternating, that's a convergent C-series. Other questions on this example? Okay. New example. So what are we going to do first? So we got a power series. And so we need to figure out, again, for what values of x does it converge. We want to find the interval of convergence and the radius of convergence. We're going to start with ratio test, okay? Ratio test. So do the first step of the ratio test. Okay, check your work. I got that up there now. Is that what you got? Agreed?
Did you do the comparison test along with it? Or on everything?
All we did is the first term of the ratio test and then started just doing algebra.
So what happens in this case?
We're not there yet. Just make sure we're all. So everyone agree with that?
Yeah.
What we did? Got a little bit of homework like this? Should feel similar to the homework. It's just we have x in there too. Okay? So you end up with x squared, and then you end up with 2n plus 3 and 2n plus 2 in the denominator. Okay, so we're ready to evaluate the limit. As n goes to infinity, what do we get inside the absolute value signs? Thoughts are saying 0. That's right. You get 0. And what was the question we were asking? The question we were asking is,
Interval of Convergence.
for what values of x does this converge?
0.
Less than 1, so for all.
So that thing has to be less than 1, right?
Yeah.
So for what values of x is the limit less than 1?
All values of that.
He wants all values of x.
Because the thing's going to explode to 0 anyway.
No matter what x is, the limit will be 0.
That's cool.
So for what values of x does it converge? Anything. All real numbers.
How do we describe the radius?
Infinite. So the interval is all real numbers. The radius is an infinitely long radius. Question?
Can you just explain the last step of algebra from where it goes from 2n plus 1 factorial to 2n plus 3 factorial?
So if you're not sure, then just write out what is 2n plus 1 factorial. Or, and better yet, what is 2n plus 3 factorial? Can you tell me what that means? 2n plus 3 factorial.
See, I forgot how factorials work.
Factorials, you start with that number, and then you take one less than that and multiply, and then you take one less than that and multiply, and then one less than that, and then you all the way to 1. Right? So it's going to be 2n plus 3 times what?
2n plus 2.
Plus?
2n plus
All right, now look, now I'm going to have 2n plus 1, and I'm going to multiply all the way down to 1. What's that? So now I'm going to start here at 2n plus 1, and I'm going to keep going down all the way 3, 2, 1.
Okay.
And what is that? The same as. I start at this number and keep multiplying down to 1. What is that when you start at a number and then you multiply by 1 less and then 1 less and then all the way down to 1? That's factorial. That's 2n plus 1 factorial. So within 2n plus 3 factorial is 2n plus 1 factorial, except for the first two terms. Factors, thank you. Does that make sense, Tyler? Okay. So it doesn't matter what x you put in here, you're going to get a convergent series. Questions on that one? Your turn for the sheet. Okay. You got 7 minutes and then I'm going on. 7 minutes, work together. Get it done.
Same question?
What's that?
Same question?
Oh yeah, so it's the interval and radius of convergence. It's the interval and radius.
So I don't know how to
What?
No, that he did his problem.
Okay, we're gonna go on. Okay, we're gonna go on. If you want to keep working on that a little bit after class, you can do that if you're not done. But we need to go on. So what we're seeing is that that's power series are example of how you can represent a function with a power series. So let's look at more examples of that. So first we want to recall this. This is what this is all based upon. Okay, so writing functions as power series is all based upon the geometric series. And remember when the geometric series converges, when r is between -1 and 1, the sum is a over 1 minus r. Okay, remember that? And this is the key to writing functions as power series. We get our function to look like that. Then we can write it as a geometric series. Okay, so consider 1 over 1 minus x. does that look like? 1 over 1 minus x looks a lot like what?
A over 1 minus r.
Does it look a lot like a over 1 minus r? Definitely, right? Definitely. With a and r equal to what?
1.
1 and x.
1 and x,
A equals 1 and r equals x. So with a equals 1 and r equals x, can you write this series? Can you write a series that equals the function 1 over 1 minus x? Can you do it?
We delete these ones.
Shell.
Well, we know what series a over 1 minus r equals, right? What does a over 1 minus r equal? We know what series that is. Well, now we got a equals 1 and r equals x. So what series does that equal?
X to the n.
Everyone should be able to do this. This is not hard. This equals this. And now we have this with a specific value of a and a specific value of r. So what series does 1 over 1 minus x equal? Oh, we're getting a c.
A is just 1.
There's no c's anywhere here.
X to the n. Just x to the n.
A is 1 and r is x. Okay, so a is 1 and r is x. Then it's 1 times x to the n. And what does that equal? 1 plus x squared plus x cubed forever, right? You keep adding these monomials with a higher power of x. Okay, but that's only true, right? So we know there's this interval of convergence for geometric series when r is between -1 and 1. And if r is x, then x has to be between -1 and 1 for this to equal this. So this is a way of rewriting a non-polynomial function kind of as a polynomial, but it's going to take an infinite number of terms, and it's only going to work between -1 and 1.
That's amazing.
So let's see it. Let's see how amazing it is. Can I?
You're writing a function as a sum.
Yeah.
This is crazy.
Well, an infinite sum, right? Lots of functions are sums,
Right.
but an infinite sum. So let's take a look. Let's take a look at that function 1 over 1 minus x. Okay, so here's 1 over 1 minus x. So we can get approximations of this series with what's called partial sums. Partial sums is the first, say, the first n terms. Okay? And the longer your partial sum, the better approximation it is, right? Because if it's a convergent series, what happens to the terms? They become like what? If it's a convergent series, then your terms must become like 0, right? So, and they're getting smaller and smaller. So you have an approximation for the first n terms, and then the more that terms you add, the better and better your approximation becomes. So let's just start with y equals 1 plus x. Okay? This is the second partial sum, because it's only adding the first 2 terms. You see that? So let's make these distinctly different here. We'll put the actual function. So the red function is the first partial sum of our series there, 1 plus x.
It's a bad approximation.
All right, bad approximation. But can you see that it's trying to approximate our blue function in the range from -1 to 1? Can you see that it's kind of doing it? Okay, so let's add 2 more terms. So I'm going to add x squared, and then add x third. So this is our 4th partial sum. First 4 terms. right? So the red one is our series version. That's an approximation to the series. And the blue one is the original function. And you see that within, let's go ahead and do this. Are you colorblind?
Yes. No, that looks like a purple. Because the other one looks blue, like right next to green.
Let me try something different here. So what colors do you have a hard time distinguishing?
Red.
I can like distinguish it, but I just thought it was purple.
This one?
Yeah.
Yeah, it's kind of got a purplish tint to it. All right, so this one, the one that you think is purple or blue, that is the actual function 1 over 1 minus x. The red one is the fourth partial sum of the series that we found, that we said converges if you're between -1 and 1. So let's add 2 more terms.
The boundary cell.
So we'll add x to the fourth and x to the fifth.
Oh,
So what's happening between -1 and 1?
matches.
It's converging to the curve. Outside of -1 and 1,
Doesn't matter.
if there's nothing, there's no similarity, right? So greater than 1, there's no red anywhere, right? Less than -1, this thing, they're diverging from each other, right? But between -1 and 1, the more terms I add, the better approximation my series is, the more it converges to. One more for kicks. This is the 11th partial sum.
Man, that's so close.
So it's like they're just on top of each other now, right? And to our view, they're so close in this view that they're on top of each other. Well, so it's depending on if you end with an even or an odd, it's either going to flip down. So if I add one more, it'll flip down. And if I have an x to the 12th, it'll flip back up again.
And it'll keep flip-flopping.
It flip flops, yeah.
Oh, man.
So if I add one more term, it will flip down at the end.
You're a wizard. This is insane.
What if you add plus x to the 100?
That won't do anything because each of these terms are getting smaller and smaller and smaller. So adding x to the 100th isn't going to do anything to this because its magnitude will be like so small compared to the ones we have. It won't do anything. Okay, and so if you were to add all infinite number of terms, you would have exactly, the functions would be on top of each other. It would be, the red one would be on top of the blue. But this is a very, very good approximation when you have, this is 13 terms. Okay, cool stuff. Okay, so let's do another one. Maybe. There we go. Okay, so we want to write x over 2x squared plus 1 as a power series and find an interval of convergence. Okay, so we've got to make that look like what? It has to look like a over 1 minus r, or we can't do it. If it's anything else than a over 1 minus r, we can't do it. So can we get a over 1 minus r out of this? Well, we got a fraction. We absolutely need to have a 1 here, and it has to be minus. So minus what? 2x squared. Is that the same as this? No, 1 minus 2x squared is not the same as 1 plus 2x squared.
Negative 2x.
1 minus negative 2x squared. Is it the same?
Yes.
Does that equal that? And is it in the form a over 1 minus r? Okay, so I wanna do something else here. You don't have to do that here, but just for future examples. We could also just work on, if we could just find the power series for 1 over 1 minus 2x squared. And then in the end, what would we do?
Multiply it by x.
Yeah, we could just take the series that we find and just multiply it by x. So we can either say a equals x, or we can do this one with a equals 1, and then at the end, just multiply by x. Both ways work. So we can have any kind of a monomial of x multiplied, and then we can just multiply that by the series that we get. And if we did 1 over 1 minus 2. So let's do it this way. So then we're going to just multiply by x at the end. Okay, so what is so this equals, what series is equal? Negative 2x to the 2n.
No. Negative 2. How do you distribute that n?
1 plus.
Or do you just leave it?
I don't know what you're talking about. So we're just going to write down what this is.
N equals 0.
N equals 0 to infinity of what? Not 1 over anything.
X over
Oh.
Not there's no over anything, you guys.
Quantity negative 2x squared to the n.
A r to the n. A r to the n. So what will it be?
Negative 2x squared times 1. Yes, it's going to be negative 2x squared.
To the n.
To the n, right? To the n. 1 times negative 2x squared to the n.
We just leave that.
No, so we gotta finish, right? Right? What do we need to know?
So is it negative 2 to the n times x to the n?
Okay, I'm not talking about simplifying this. I'm saying, what do we need to find out?
Ratios?
For what?
Convergence.
Yeah, so we need to find the interval, so now we need to find the interval and radius of convergence.
And where's the n you're talking about when we multiply by x?
The end of the solution, whatever we get. So we could do it right now.
Okay.
Right, and we better do that if that's going to be part of, yeah. Right. But we need to do that before we do the. And so now we're gonna apply. So this series is for this. And what do we need? We need x times this, because our function is x times. So g of x equals x times negative 2x squared to that. And that's important for our interval of convergence. So here it's like there's like almost no difference between multiplying by x when you're done versus letting a be x, right? So we could have just said a equals x, and then we'd have this a times r to the n.
Is there a situation where that wouldn't work? Like you can't just kind of pull out x early on, multiply it out, and have it be 1 over 1 minus.
Yeah, so I'm alerting you to that strategy, which on more complex problems will be advantageous. Yeah, but in this case, it's like 6 of one, half dozen of the other. It doesn't really save you anything, but just be aware of that. That you can do this one, and then once you get that series written, boom, x. Okay, so then we have to figure out when this thing converges. So we want to pull this apart so it looks a little more. Want to like group all our x's together, and then we'll have like negative 2 here, negative 2 to the n, and then we'll have x to the what?
X to the not the same 1.
As the
No. No one's close yet. I have an x, and then I have an x squared to the n. So when I combine all these x's, I have an x and x squared to the n.
So it's going to be x to the 2n plus 1.
Okay, so this is x to the 2n, and then we have one more x. No, this is x to the 2n.
So x cubed times
So
x.
2x.
No, you can't add this. This is to the 2n. You can't make it cubed. This is to the 2n, and then we have one more. 2n plus 1.
Oh, there you go. Correct.
2n plus 1 is not 3. Okay? 2n plus 1 is not 3. Okay, so now we can do ratio test. Figure out what we got here. So we're going to have negative 2 to the n plus 1 over, doing red, negative 2 to the n plus 1 over, or times x to the, that'll be 2n plus 3 over negative 2 to the n, x to the 2n plus 1. So we're going to get negative 2x squared.
You would have gotten the same had you not distributed the x.
Right? But they're all, so it's just cleaner to put all your x's together. If you,
But if we're dealing with limits with n, I would rather just keep the x separate because I know it's going to cancel. If I just have x to the 1 and
Okay.
x to the 1.
great. Okay, and so we need that thing to be less than 1. So that means between 1 and negative 1. Or actually, so the negative 2 can just be 2, right? Absolute value, right? So absolute value of negative 2x squared is just 2x squared. So 2x squared has to be between negative 1 and 1. Which means that
So
x squared between half and negative a half.
the roots, huh?
And so x is between square root of a half, which is the same as
Oh,
radical 2 over 2. And square root of negative,
Well, we don't want to take square root of negative.
no, it's not, you're not taking square root of negative. You can have a negative value squared. Yeah, I mean, you're asking for what are all x values such that if you squared them, you'd be between these two values. Or less than 1, basically. So what we could have done is this. So this has to be positive. So we could have said, we could have done this.
Yeah.
Because that has to be positive. So what x values give you between 0 and 1/2? Well, negative radical 2 over 2 to positive radical 2 over 2.
So we shouldn't have the negative 1, negative 1/2.
It's just redundant. You can if you want.
The plus or minus, right? Let's say one around it.
This is always positive because it's squared. Once you square it, it's always positive. So it doesn't matter. You could put the negatives here, the negative radical 2 or 0. But we're asking what values of x are in that range. Well, then you have to include negative values of x because when you square them, they're positive. Okay?
so this is the radius of convergence.
This is the interval of convergence. And then we'd have to check, we don't have time, but you'd have to check for check n values. We want to go on to another example. But what you would do is you'd plug x equals negative radical 2 over 2 into this, simplify it, and evaluate for convergence or divergence. Plug in positive radical 2 over 2. And evaluate it for convergence or divergence. Yes, sir?
Why is it radical 2 over 2 and not radical 1/2?
It is radical 1/2. That's the same thing. Yeah. So those are equal.
So if we put 1/2 in there, it'd be fine?
Yep.
Will we be square up the whole thing?
Yeah, because you're trying to get what x is, and you have x squared.
I mean, not just the radical.
So square root of 1/2 is multiply by radical 2 over radical 2, and you get radical 2 over 2. Okay, so I want to show you something here. Let's write out some terms of this sequence, because in web work they're going to say find C0, C1, C2, C3 if you were to write it in our standard power series form. So if we were to write this like this, what would the coefficients be? What would C naught be? What would C1 be? What would C2 be, etc.? Okay, so something kind of interesting happens when you actually show what the coefficients are. So this right here, when n equals 0, you get negative 2 to the 0 is 1. You get x. So when n equals, okay, so when n equals 0, you get x. Is that right? When n equals 1, you get negative 2x cubed. And when n equals 2, you get 4x to the 5th. Is that right? And when n equals 3, negative 8x to the 7th. N equals 4. That's the ninth. Thank you. Ninth. And then finally, negative 32x to the 11th. So if we were going to write this way, what would our coefficients c to the n be? So now we're going to write it this way. So now for this is a different, ends up being a different index than this one. Because look, n equals, your n value is your exponent of x. Do you see that? So for this, your n value is what? No. Your n value is your exponent of x. So what is your n for this? So this is like n star here, because this is different n. So this is n star for this, what they want us to write it as. So n star is 1. N star is 3. It's the exponent of x. N is the exponent of x. So n star is
3.
N star is
5.
5. N star is, okay? So then what is the coefficient when n star is 0? So what's C0 then? So Cn is, what is C0?
1.
No, it's 0 because there is no x to the 0.
Oh, right. Yeah. Okay.
What is C sub 1?
1.
So C sub 1 is when your exponent is 1. It's the coefficient when the exponent is 1. What is that? 1. Then when the exponent is 2, what is your coefficient? Here's what we're recreating.
We don't have an exponent.
Right, so what coefficient do you need when the exponent is 2?
0.
0.
What is that?
So C0 is 0, C1 is 1, C2 is 0. All right, now, when we have an exponent of 3, what is the coefficient?
-2.
-2. When we have an exponent of 4, what is the coefficient?
0.
0. There is none. When we have an exponent of 5, what's the coefficient?
4.
4. When we have an exponent of 6, what's the coefficient?
0.
Exponent of 7, what's the coefficient?
-8.
So this is how you'd have to put these coefficients in. If they want you to write this power series in this form, then anything with an even exponent has a coefficient of 0, because there are no even exponents in that power series. Is it making sense?
Yeah.
So it's just 0 if it's not, like if n star isn't one of our values, basically.
Yeah, so it's only made up, this power series is only made up of odd powers of x. But if you write it in this form, you have every power of x. So whenever n is an even value, you're going to have a 0 coefficient, so that there's no term.
Oh, okay.
But whenever you have an odd power of x, that's when you have these coefficients. 1, -2, 4, -8, 16, -32. So these are the Cn values if you need to write it in that form, and that's a common thing in web work. Does that make sense?
Yeah.
So let's try another one of these.
It's just like the long division where we have the placeholders.
Okay, so here, what do we have here? 3 over 1 minus x squared. What do we need it to be like?
A over 1 minus well, minus r.
We need it to be like a over 1 minus r. Is it?
Yeah. So we're good.
Andre says, yeah. Agree with that?
No.
Oh, I didn't see the quantity. Okay.
Yeah, this is different now. This is different. So we could think, okay, maybe we should multiply this out, right? 3 over 1 minus 2x plus x squared.
Maybe we should.
How about now?
Yeah. You just group it, then put a negative in the middle.
Just 2x plus 6 squared.
Okay, but let's think about that. Let's think about that. We're going to eventually say this is equal to what? A r to the n.
We can't have R be some expression.
You can't have an r be a sum.
Oh, that's not allowed.
No, because what happens?
The a times
I
something.
mean, what happens when you get to the 10th term?
Right?
Right? What happens when you get to the 100th term, right? You have a binomial to the 100th and a binomial to the 101st. Okay?
So it's not illegal, it's just inconvenient.
Okay, absolutely.
Yeah, no, it's bad. Okay. So what do we want? So here, we have to be a little. So we're not going to do that. We have to be a little ingenious here. So how could I? What do I want to say? What variation on this? What variation on this? Think calculus is like a over 1 minus r. What variation on this? The derivative. If you took the derivative of this, would you get 3 over 1 minus x? No, you get 3 over 1 minus x to the... If you took the derivative of this. If you took the derivative of this, what would you get? 3 over 1 minus x to the... That would be to the third, right? Because you lower the power, right? This is the negative second power, you'd lower the power. So what about taking the derivative of this?
Bad idea.
Goes the wrong way, right? So what can we do to make it look like this? Integral, right? So if we do the integral with the antiderivative, Should be easy. Okay, dx is important, right? Dx. We would have 3 over 1 minus x, right? Because we're raising power. Hold on to the constant, raise power. Is this the antiderivative of this? Or do we have a mess to clean up here? If you were to take the derivative of this, would you get exactly this? No. Because? Negative, right? If you do the chain rule, you also have times -1, right? So we need a negative. What about this? Can we find the power series for this? Yes. And once we find the power series for this, what will we do to get h of x?
Differentiate.
Take the derivative. Because this is the antiderivative of what we want. So we can find the power series for this and take its derivative, and that'll be h of x. Pretty cool, huh? All right, so this is a pretty easy one here. A equals? A equals -3. R equals? X. So that's pretty simple. So -3 over 1 minus x is equal to the sum of -3 times x to the n, or n goes from and now what's very helpful in these problems is to write out some terms, okay? So see this, we think what, right? See this, think what?
I think
-3
plus or minus, minus 3x.
3x minus 3x squared minus,
Minus 3x.
and so on. So what are we going to do? So this is the antiderivative of h. All of these represent the antiderivative of h if x is in the interval of convergence, right? So and that will just be -1 to 1 for this one, right? Just geometric series. So then, therefore, h of x is what? So h of x means do what?
What?
All of these equal what related to h of x? The antiderivative. These are all the antiderivative. Remember? These are all the antiderivative. We took the antiderivative because the antiderivative gave us the form we wanted to able to do it. So if this is the antiderivative of h, what will we do to get h back? Take the derivative. Okay, so we're going to take the derivative of all these, and we know that's our 3 over 1 minus x squared. Okay, and so we can just take the derivative of that thing right there. So now we want to, I like to hold off on where n's going to start, okay? But what's the derivative of -3 times x to the n?
-3 and x to the n minus 1.
-3n x to the n minus 1. Now let's do it term by term. What's our derivative here? 0 minus 3 minus 6x 9x squared. Let's do one more. It'd be 3x to the 4. So yeah, 12x cubed. Okay, so the question is, we need to reconcile what n's going to start at with whatever expression we have there, so we get exactly these terms, right? This is the right series. So we just got to make sure this thing matches this series. Okay, so we could just, if we put n equals 0 here, would it work? When n equals 0, we get 0. When n equals 1, we get -3. So we could start by just saying n equals 0, and that works. We get exactly those terms over there. But now if we wanted to kind of adjust this to be a little cleaner, let's see. So what if we want this to be, we don't want to just have a 0 to start with.
You could just have n equals 1, and then the exponent for x would just be n.
And okay, yep. So I'll do that in red. So we do n equals 1. Then we need, when n equals 1, we need this to be -3. You'd have to switch this too. No, that's not what I want. So my thought was, let's switch it so that for our new one, this is n equals 0, and this is n equals 1, and this is n equals 2, etc.
So,
We're rewriting this in a cleaner way. Because WebWork, so you might come up with this, and then WebWork might want it n equals 0, x to the n. Okay? So that means that this has to be the 0 term, and this has to be 1, and this has to be 2.
So you could just take out the
Okay? So if n equals 0, I need to have -3. So I need -3 times, I need 1 here when n equals 0. So what is that going to become? N plus 1. And then I need x to the n, because the power of x is the same as whatever n I have. So then x to the n. So that would be an alternate way to write this. Okay, so did you see what happened? We notice that the antiderivative has the form we want. The antiderivative was -3 over 1 minus x, so we found the power series for the antiderivative. And we wrote it all 3 ways. We wrote it as its original function, we wrote it in summation notation, and we wrote out the terms. We said if that's the antiderivative of what we want, then what we want is the derivative of that. Yeah, right. So we're going to take the derivative, and you can take the derivative on all 3 of those. We know that it's going to be 3 over 1 minus x squared. That's what we started with. You can actually just take the derivative right there of the general term. And then what I really recommend is write out the terms, take the derivative in polynomial form, and make sure that your summation form matches up, gives you exactly those terms that you find. Instead of trying to guess, do I have to adjust n or whatever, actually do the derivative on the polynomial version, and then compare that polynomial version. Whatever you write for your summation terms has to give you exactly those terms. Okay, and then we just saw the first one was 0, so if we were to shift this and make that 0 and that 1 and that 2 and that 3, then you could write it this way. Again, just write out what the terms are, and make sure you're getting exactly what you know it should be. This, you're confident about that. So whatever you put for your answer, write out what it means, and you should get exactly those terms added together.
Excuse me.
Question, yeah.
When do we know to integrate? Just when our denominator is 2?
So whatever's going to give you this. Right? Whatever's going to give you something that looks like that form.
But it seems like it's just one case when we have something squared on the bottom.
Right. Yeah. What if you had a cubed? So what if you had this over something cubed?
So we integrate twice.
You integrate twice.
That's
Okay. Integrate twice. And then you have to do what? You get your power series and then differentiate twice.
Oh, man. That sounds like a really good test question.
Oh, thanks for the idea.
No problem.
Okay, so if you want to stick around and ask questions about the homework, finish your blue sheet, you're welcome to do that, or you have to
So does then the half equal 0 for power
You
series?
got hard and